Welcome back to the next part. In this part, we have to discuss Fajans rule. Fajans rule. Okay. So Fajans rule is actually the concept of dipole moment that can be used to define the ionic character of a covalent bond. Right. Fine. So Fajans rule is used for the used to define or used to describe about the covalent character of ionic bond. Used to describe the covalent character of ionic bond. Covalent character of ionic bond. Okay, ready. We all know that in case of an ionic bond, if this is your cation, positively charged cation, and this is your anion. Okay. Now, during the formation of an ionic bond, cation completely lost the electron and anion completely gained the electron, right? And cation occurs a positive and anion occurs a negative charge, right? But cation is smaller with a greater force of attraction, right? So there is a chance for attraction. There is a chance for the attraction of electron cloud from anion to cation. There is a chance for the attraction of electron cloud from anion to cation. So that what happened means when the electron density come towards or moving towards the cation due to the attraction of this cation, then the shape of anion get distorted. The shape is distorted because that particular electron density, here is the electron density. When that electron density attracted by the cation, the electron density distorted towards what? Cation. Ready? And this particular type of distortion, this is the electron cloud. Okay? And this particular kind of distortion called polarization. This particular type of distortion called polarization. So due to polarization, what happened means the donated electron may brings in between or maybe in between cation and anion, right? The donated electron may held in between cation and anion, which increases the covalent character of the typical ionic compound. Okay, so ionic bond means there is a complete loss and gain of electron, but due to the attraction of the cation, electron cloud is distorted towards cation, and it arranged between both cation and anion, which increases the covalent character of that bond. Okay, so you have to know some kind of terms here. Polarization, okay, phenomenon of distortion of electron cloud from anion to cation. So phenomenon of distortion of electron cloud from anion to cation. Okay, ready. Number 2. If the electron cloud is more distorted towards cation from the anion, which increases the covalent character. Okay, greater the polarization, the covalent character increased. Covalent character proportional to polarization. Ready? Covalent character is directly proportional to polarization. Is it okay? Fine. Number 2. Polarizing power of cation. Polarizing power of cation. So what is the polarizing power of cation? polarizing power of cation is, here cation have a role for the polarization. Cation have to attract the electron density from anion, right? And that tendency or the ability of cation to attract the electron density from anion is said to be polarizing power of cation. So polarizing power of cation is the ability of cation to attract the electron density from anion, or ability of a cation for polarization. You know, the polarization is the process of shifting of electron cloud from anion to cation. And what is the role of cation? That means cation have a role to attract that electron cloud from anion, and that is said to be the polarizing power of cation. And the third point, and it is clear that polarizing power of cation that is proportional to polarization, right? Polarizing power of cation that proportional to polarization. Because greater the tendency of cation to attract the shared electron density, greater the chance for polarization, right? And the third term that is polarizability of anion. Polarizability of anion means it is a tendency of anion to undergo polarization. Tendency of anion to undergo polarization. Okay, it is the tendency of anion to undergo polarization. And one thing is clear, if the nucleus of cation have greater force of attraction, there will be a greater polarizing power of that polarizing power by the typical cation. Similarly, if the nucleus of anion have greater force of attraction, then electron cloud will not distort to the cation. So if anion have a greater force of attraction from its nucleus, then electron cloud is always held by what? Anion. So here the anion should, the force of attraction from the nucleus of anion will be comparatively lesser. Okay, comparatively lesser. Ready? So force of attraction of cation should be higher, whereas force of attraction of anion will be comparatively lesser. So polarizing power of cation that is proportional to polarization, that's okay. And the main point that is polarizing power of cation that is proportional to force of attraction of cation. Greater the force of attraction of cation, greater will be the polarizing power. Force of attraction of cation. Force of attraction from the nucleus of cation. Okay, ready. Similarly, if your anion have great tendency to undergo polarization, means the force of attraction of your anion will be comparatively lesser. Okay, so the point is that listen. Polarizability, as the tendency for polarization increases, what happened? Polarization increases. As polarization increases, covalent character increases. Polarization increases, and this polarizability that is proportional to force of attraction, that is not proportional, that is inversely proportional to force of attraction of nucleus, force of attraction of anion. Force of attraction of anion. Okay, if the force of attraction of anion is comparatively lesser, then polarizability increased. Now let's find the statements from Fajan's rule. Okay, statement number 1. Statement number 1. Smaller cation, greater covalent character. smaller the cation, greater the covalent character. Smaller the cation, greater the covalent character. Ready? Fine. Smaller the cation, greater will be the covalent character. The reason behind that is size of cation decreases. As the size of cation decreases, we know that if the size of cation decreases, its force of attraction increases. Force of attraction of cation increases. Automatically, polarizing power, the tendency to attract the shared electron density, donated electron density will increase. Polarizing power increase. If polarizing power increase, polarization increased. If polarization increased, automatically covalent character increased. This is the reason. Okay, this is the reason. So let me give an example. Okay, so covalent character, let me see covalent character of following. I have NaCl, KCl, CSCl, RBCl. What about the covalent character? Here all cations are same. Sorry, all anions are same, and the charge of an is also same. The difference is the size in anion. So covalent character will be like this. So from left to right, size of cation increases, covalent character decreases. Ready? So smaller the cation, greater will be the covalent character. Here the smaller cation, so greater will be the covalent character. This is the first statement, and this is a necessary explanation. If the cation is smaller, then its force of attraction will be higher. If its force of attraction will be higher, then it have a greater tendency to attract electron from anion, which means polarizing power higher. Polarizing power is higher, then there is a greater polarization, right? Electron density distorted from anion to cation, so that the covalent character increases. Okay, fine. Move to the next point, very same point from cation itself. Greater the charge of cation, greater the charge of cation, greater covalent character. Greater covalent character. And the reason that is, positive charge increased. We know that cation with a greater positive charge is smaller. Positive charge increased, size decreased, force of attraction increased. Size decreased, force of attraction of cation increased. Automatically, polarizing power increased, polarization increased, covalent character increased. This is the reason. Okay, so I can show you the example regarding this one. The example is that I have NaCl, MgCl2, AlCl3, SiCl4. These all are my compounds. Here Na plus, Mg2 plus, Al3 plus, Si4 plus. These all are the order. Okay. Both the cations are same. Sorry, anions are same. And cations are isoelectronic, but the positive charge is increased. So greater the positive charge, greater will be the force of attraction. Okay. So this will be the order of covalent character. Okay. As per Fajans rule. The next. The next idea, that is regarding anion. Okay, larger the anion, greater covalent character. greater covalent character. And what is the reason? Size of anion, as the size of anion increases, its force of attraction decreases. If the force of attraction of anion decreases, then anion is allowed to withdraw, or anion is able to withdraw its electron density towards cation. Okay, since its force of attraction is weaker, which means the polarizability of anion higher. So force of attraction decreases means polarizability of anion that increased. As the polarizability increased, the phenomenon of polarization increased, automatically covalent character increased. Okay, so I'll give you example. If I have NaF, NaCl, NaBr, Nai. What about its covalent character? This is the covalent character, because here the cations are same, anions with the same charge, but the size of anion increases from left to right. So from here to here, size of anion increases. Automatically, as per Fajans rule, covalent character increases. Okay, this is a necessary explanation, you know. Moving to the fourth point. Greater charge of anion. Greater the charge of anion, greater covalent character. Greater the charge of anion, greater is the covalent character. Okay, greater is the covalent character. Then what is the reason? The reason is that greater the covalent character, greater the charge of anion, greater is the covalent character. Fine. So greater negative charge. As the negative charge increases, what happens? Size increases. Anion with greater negative charge will be larger. You know that point from classification of elements. Size increases. As the size increases, what happens? Size of a substance increases means its force of attraction decreases. If force of attraction decreases means in terms of anion is a tendency for polarization increases. Polarizability of anion increases. If the polarizability of anion increases, polarization increases, covalent character increases. Okay, so let me give examples. If I have sodium fluoride, sodium oxide, sodium nitride, sodium carbide. Don't know whether it is sodium carbide exists as stably, but in a theoretical aspect we can consider. Fluoride, oxide, nitride, carbide. So here the anions are same. Okay, from left to right, the charge of anion increases. So covalent character also increases. Okay, fine. And the last fifth statement: two cation with similar shape and charge, then one with pseudo noble gas configuration, What is actually the pseudo noble gas configuration? Pseudo noble gas configuration means noble gas followed by noble gas followed by NS2 N minus 1 D10. This is pseudo noble gas configuration. More covalent than noble gas configuration. You know, noble gas configuration means simply a noble gas configuration. And what is the reason? Like, the reason is that, listen, here the last electron, noble gas configuration means that is NS2 NP6, right? Here the last electron in poor shielding d orbital. For the shielding of d orbital, force of attraction of that cation higher. Poor the shielding, greater the force of attraction. Here the valence electron is in well shielded p orbital. Okay, so poor shielding which brings greater force of attraction in cation, so greater polarizing power, greater polarization, greater covalent character in pseudo noble gas configuration. Okay, fine. For example, if I have CaCl2 and CdCl2, here calcium is in 2 plus, where this have a configuration of argon. Okay, argon or otherwise neon followed by 3s2 3p6. Cadmium, zinc, cadmium, right? Okay, so cadmium, zinc have atomic number of 30, cadmium 48. 48 means krypton 36 followed by 5s2 4010. 5s2 4010. This is the configuration of cadmium. So this is a pseudo noble gas configuration. This is a perfect noble gas configuration. So more covalent species is here. The configuration of CD2 plus is like this. Okay, CD2 plus means I think these 2 electrons will be lost. Okay, so CD2 plus. This one have greater covalent character than this one. Okay, simply transition metal compound have greater covalent character than S block metal cation or S block metal compound. Okay. So this is said to be Fajans rule. Resonance. We know that we are already familiar with the resonance concept in your organic basic principles. So write down. Actually, resonance is used to describe the Hall property of a molecule. Okay. In order to describe the Hall property of a molecule, a single Lewis structure is not enough. So we use more than one Lewis structure, and the Lewis structures are called resonance structures or canonical structure. Okay. So why the resonance means it is used to describe the Hall property of molecule. So write down. It is used to describe the Hall property of a molecule. Okay. Next point. For that, we have to represent the molecule in more than one Lewis structure. Second point, for that we have to represent the molecule in more than one Lewis structure called resonance structure or resonance structure in bracket RS or canonical structure resonance structure in bracket RS or canonical structure. Okay. We all know that benzene have 2 different resonance structure. In order to explain the Hall property of benzene, it requires 2 resonance structure because these 2 bonds are actually not 2, not 1. These 2 bonds are actually 1.5. So in order to explain the bond order of that benzene carbon bond as 1.5, you require these two canonical structure, because 2, 1 is there. So actually in between that is the bond order, that is 1.5. Okay, so you required more than one Lewis structure. Ready? Fine. And these all structures are called, this 1 and 2 structure are called resonance structure. This is not actually existing. The actual existing structure is the most stable hybrid structure. Okay, so you copy the next point. Resonance structure have no real existence. Resonance structure have no real existence. Resonance structure have no real existence. Next point. The molecule really exists as a hybrid structure. The molecule really exists as hybrid structure. In bracket, most stable. In bracket, most stable. What about the next point means? Your each canonical structure have a definite contribution to hybrid. Okay, and the canonical structure one with more stability can contribute more. That's the point. So next point. Each canonical structure have, or each RS, resonance structure, let it be RS. Each RS have a definite contribution to hybrid, in which the most stable RS contributes more. In which the most stable RS contributes more. Okay, next point. Usually RS with less formal charge. Usually RS with resonance structure with less formal charge. Stable octet. Stable octet. Electron pair in more electronegative atom. Usually RS with less formal charge. Stable octet. Electron pair in most stable atoms are relatively more stable than others. So you know that resonance structure with more stability can contribute more to the hybrid. Then how can you compare the stability of resonance structure means, if there is a resonance structure one with the least formal charge, listen, one with the least formal charge, let this be the butadiene. The formal charge is 0, right? And if we consider the resonance structure of this one, okay, when this bond jumps to here, this may jumps to here. So it become CH2 minus single bond, CH double bond, CH2 plus. So this have formal charge. So this have formal charge. These are canonical structure. This is 1 and this is 2. So what about the stability means? Resonance structure with the least formal charge. Here all have 0 formal charge. So 1 is more stable than 1 with the greater formal charge. Okay. The next idea, if you consider the octet of this one, a carbocation only 6 electron, where octet is not complete, where all others have complete octet. If you consider the resonance structure like this, now your carbon is okay, and here is a double bond, here is a positive charge, CH3. Now your carbon have 8 electron, moreover the positive oxygen also have 8 electron, 2, 2, 2, 2. So in this structure all are all completes octet. Second structure. So stability of, if this is 1, this is 2, stability of 2 is greater than what? 1. Because 1 with the greater octet is more stable. Ready? The next idea, if I have a structure like this, CH3, C double bond of CH2 minus, let me consider the resonance structure of this one. If this jumps to here, this is to here. So CH3, CO minus, double bond CH2. So which one is more stable means here the negative charge in more electronegative oxygen. Here the electron pair is in more electronegative oxygen, but here the electron pair is in less electronegative oxygen. So 2 is more stable than what? 1. So these are the different F criteria used to describe the stability. Okay. So let me write the next point. So next point. The energy difference between most stable canonical structure and energy difference between most stable canonical structure and resonance hybrid called resonance energy. Let this is a resonance structure 1, this is a resonance structure 2. If I am plotting energy here, this is a hybrid. Okay. If energy increases means stability decreases. So RS2 is the most stable RS, right? Most stable canonical structure is this one. Because comparatively, comparing with the RS1, energy of RS2 is relatively less. Ready? And the very most stable form of that molecule is said to be hybrid. Then what is the energy difference between the most stable canonical structure here, that is RS2, and hybrid? That energy is said to be resonance energy. That energy is said to be resonance energy. Okay, and we can find the bond order also. Bond order is total number of bonds between two atoms in all canonical structure. Total number of bonds between two atoms in all canonical structure divided by number of canonical structure. Divided by number of canonical structure. You obtain the bond order. Okay, listen. So bond order equal to total number of bonds between two atoms in all canonical structure. Fine. Wait. I'll give you examples for some. If I have benzene, there are actually two canonical structure. Okay, so let me find the bond order of these two carbons. I think these two are same. Fine. So let me find the bond order. Bond order is equal to number of bonds between two atoms in all canonical structure. Number of bonds in this canonical structure, that is 2. Number of bond between the very same atom in this canonical structure, that is 1. All divided by number of canonical structure, that is 2. So that is 1.5 is the answer. 1.5 is the answer. Now, carbonate. We know this is a Lewis structure of carbonate, so it can show resonance. When this jumps to here, this may jumps to here. So here will be the O minus, here will be the O minus, here will be the double bond. When this jumps to here, I'm sorry, ready? When this jumps to here, this may jumps to here. So the third canonical structure will be like this. Okay, and you know the equivalent hybrid structure of this one. The electron density moving like this. Here is a O. Ready? Fine. Oh wait, and this is written for bond order, right? Bond order of carbon oxygen bond. Bond order of carbon oxygen. Here the number of bond 2. Here the number of bond 1. In this canonical structure between the very same atom bond, all divided by 3. So 4 by 3 is the bond order. 1.33 is the bond order. Okay. What about the resonance structure of CO2? This is a normal stable Lewis structure of CO2. But the CO2 also have a structure like this. When this jumps to here, this may jumps to here. So here is oxygen with a triple bond, or that oxygen have a positive charge, and here is the oxygen with a single bond, negative charge. But this is more stable. Okay. One more structure will be there. If this may jumps to here, this bonds to here. It's counter structure. Okay. So this is how your resonance involved, and you will discuss. You may familiar with the idea of resonance deeply in your organic chemistry.